3 students. This is definitely my last video lecture for this assignment and for this course, okay? The problems that I would like to do, oops, there's one thing that I forgot. Hold on 1 second. Oh, come on. Okay, 1 second here. Okay, so the problems that I would like to do for this video lecture are as follows. We are going to do problems 87, 88, 90, 91, 92, and finally 95. Okay, these are all line integral problems. So as I promised, I am doing one last video lecture that is completely devoted to line integrals, okay? So those are the 6 problems that I would like to do. And hopefully we can get it done within about an hour or so. I don't want the video to be longer than an hour. So let's try to get through these 6 problems. And we should be able to, okay? All right, so let's start with problem 80. Oh, did I say 87? So I'm on problem 88. Okay, here we go, 87. Okay, problem 87 reads, find the average value of the following function on the given curve. So we have f of x and y is equal to x plus 2y on the line segment from the point 1, 1 to 2, 13. Okay, so not that difficult. Okay, so the first thing we're going to have to do is we need to find a parametric representation. We need to find a parametric representation of the line segment that connects these 2 points. And that's going to be pretty easy to do. You know, that should be pretty easy to do. So what we're going to do is, let's see, r of t is equal to 1 plus 2 minus 1 is 1, so 1 plus t, and 1 plus 13 minus 1 is 12, 12 times t. And shift enter. Okay, let's try it. R of 0 should give me 1, 1. And R of 1 should give me 2, 13. Okay, terrific. So this is the equation. This is the equation of the line segment. This is the equation of the line segment with the understanding that t must have a value between 0 and 1 inclusive. Okay, so t could be 0, t could be 1, t could be 0.1, t could be 0.99, okay, but t must have a value between 0 and 1, because otherwise this equation is not true. Okay, so that looks pretty good. Now let's define f of x and y. F of x and y, excuse me, is equal to x plus 2y. Okay, so that looks really good. Now the thing is, this is an example of a scalar. This is called a scalar line integral. It's a scalar. Why is it a scalar line integral? It would be a vector field line integral if I had something like this. You know, f of x and y is equal to, using Mathematica notation, you know, x comma 2y. But that's not what we have here. So this is called a scalar line integral, and it's a little bit different, just slightly different from, you know, the vector field line integral, okay? So here we have to make some substitutions here, okay? So first of all, f of r of t, okay, so that's going to be the x value, okay? So what am I doing there? R of t1 is 1 plus t. 1 plus t is the x component of r of t. One plus 12t is the y component, or the second component of r of t. 1 plus t, here, let me do this one more time. Okay. This is the x component, or first component, of r of t. Okay. This is the y component, or let me see. This is the y component, or second component of r of t. So I hope you see that. Okay, so then what I have here is f of r of t, okay, the x component of r of t, and the y component of r of t. And we can expand that. 3 plus 25t. Okay, terrific. However, I need to find the norm of the derivative of r of t. Let me write that down. I must find the norm, or magnitude, of the derivative of r of t. Okay, and how do I do that? Well, I think I showed you in my last video. All right, so derivative with respect to t, r of t. That's easy. Okay, that's 1 and 12. What about the norm or the magnitude? Norm, comma 2. Okay, there are different norms, by the way. There are several different norms. The traditional vector norm used in a calculus 3 class is called the Frobenius norm, or the 2 norm. Okay, there are several different norms. The traditional vector norm used in a calculus 3 class is called the Frobenius norm or the 2 norm. So we can see that that value is the square root of 145. Okay, it's simple. We're ready to do the integral. We're ready to do the integration. Escape, dint, escape, okay, parentheses, okay, the square root of 145 times 3 plus 25t, or 25 times t. Okay, and actually I don't have to write times here, I could just use a space. You know, that's acceptable. Whoops. I'm integrating with respect to t, and my limits are simply going to be 0 to 1. Shift, enter. Okay. Oh, and you know what? There's one thing that I forgot to do. Pearson will not accept this answer because, okay, this is a partial answer. In fact, you know what I should do? Hold on one second. Answer 1 is equal to, okay, I have to take this value, okay, I have to take this value 31 times the square root of 145 divided by 2, and I have to divide it by the length of this curve. Now, finding the length of a line segment is really easy. Finding the length of a line segment should be very easy. You don't need to know any calculus to do that. That's pre-calculus or, you know, high school geometry. Okay, so let's see. Put my cursor back here. Answer 2 is the square root of 2 minus 1 squared, or I could do control 6 squared to make it look prettier, plus 13 minus 1 squared. So here I'm finding the length of this line segment. I'm finding the length of the line segment. So that's the square root of 145. Okay, so then I simply take answer 1 divided by answer 2, and I get 31 halves. 31 over 2. 31 halves, or 31 over 2. Okay. Not so bad, right? Next question. Let's see. Find the average value of f of x and y is equal to the square root of 4 plus 9y to the power 2/3 on the curve y is equal to x to the power 3 halves on the interval where x falls between 0 and 5 inclusive. Okay, so let's get to it. Okay, so first I'm going to clear my definitions of f and r to avoid any possible conflicts. Okay, so f of x and y is equal to the square root of 4 plus 9 times y to the power of 2/3. Shift enter. Now here's the tricky part, okay? We need to find a parametric representation of this curve. Okay, we need to find a parametric representation of this curve. It's really not hard, guys. Okay, here's the way to do that. Okay, r of t is simply equal to t, so the x part is t, and then y is equal to t to the power 3/2. And there you go. That's the parametric representation of that curve. That's the parametric representation of that curve. So x is simply equal to t, or t, I should say t is equal to x, but it's really the same thing. X is equal to t, or t is equal to x. Y is equal to x to the power 3/2. Therefore, y is equal to t to the power 3/2 because x is equal to t. And if t is really the same as x, t is really the same as x, t is equal to x, so x to the power 3/2 is therefore the same as t to the power 3/2. So I think it makes a lot of sense. Hopefully it makes sense to you as well, okay? We're going to proceed just like before, okay? So we have norm, derivative. I'm finding the derivative of these functions with respect to t. Let me enclose that in parentheses. R of t. Okay, so I'm getting this absolute value of t thing. Okay, but I don't really need it because t is not negative. T is not negative on its interval. Okay, t, which is the same as x, is between 0 and 5, right? So there is no need to use the absolute value function in this case, is there? Okay, so we can get rid of that. We can get rid of that by doing this. Full simplify. Full simplify. Assuming that t is greater than or equal to 0. There we go. So now we just have the square root of 1 plus 9t over 4. And that's pretty simple. So what are we going to do here? Okay, so let me clear answer 1, answer 1, answer 2. So answer 1, which is the numerator, okay, that's going to be, let me see, the definite integral. Okay, the definite integral, okay, I should really use parentheses here, of f of r of t1 and r of t2 times times the square root, here, let me expand this a little bit, times the square root of 1 plus 9t over 4, okay? And let me see, I'm integrating with respect to t, and my limits are 0 and 5. Those are my limits. So 265 over 4. However, that looks okay. However, excuse me, we have to remember that we're looking for an average value of the function, which means I need to divide this integral. I need to divide this integral by the length of the curve. I need to divide the integral by the length of the curve. Well, how do you find the length of a curve? So that should be easy. You guys should remember that from the beginning of Calculus 2. How do I find the length of a curve? Well, we can use the formula. One second. Escape d int escape. Okay, so this is going to be the square root of 1 plus the derivative of t to the power 3/2. Or if you prefer, we could use x. I mean, it really doesn't make a difference here. 3/2, and I'm differentiating with respect to x, raised to the power 2. My variable of integration is x. And I'm integrating on the interval 0 to 5. Okay, and this is actually going to be my denominator, or answer 2. This is answer 2. Okay, let's see what we have. Answer 1 divided by answer 2. Shift enter. Okay, so that looks like kind of a weird answer, but I think that's the right answer. The average value is, let me see something. Yeah, that's kind of a weird answer, but I think that's correct. 1,431 divided by 268. Yeah, usually, usually the answers to Pearson's problems, if it's a fraction, it's usually a simpler fraction than that, but sure, I mean, of course that could be the answer. It doesn't have to be 1/2 or 2/3 or, 1/8 or 1/9. It could be a more complicated fraction, right? Okay, that looks good. Let's see. We have 4 more problems to do. Let's take a look at problem number 90. Let's take a look at problem number 90. Okay. So guys, I'm going to start kind of picking up the pace a little bit. How long is my video so far? It's about 24 minutes. So yeah, I don't want this video to be longer than 1 hour, okay? So yeah, so I'm going to have to start picking up the pace a little bit. So number 90 reads, convert the line integral to an ordinary integral with respect to the parameter and evaluate it. And I'm pretty sure, let me see something. 91, 92, Yeah, I believe 90, 91, and 92 are all pretty similar, and then 95 is a little bit different. So, okay, okay, here we go. So number 90 reads, convert the line integral to an ordinary integral with respect to the parameter and evaluate it. Okay, so the function is x times y times z, and the line segment is from 0, 0, 0 to 1, 4, 6. Okay, so that looks pretty easy. 1 second, let me move that over a little bit. Okay, so we're going to clear F and R and answer 1 and answer 2. Okay, so we have f of x, y, and z is equal to x times y times z. And then r of t is equal to, okay, so that's just going to be t, 4t, and 6t. Okay, because, well, it's really going to be 0 plus 1 minus 0 times t. And this is going to be 0 plus 4 minus 0 times t. And this is going to be 0 plus 6 minus 0 times t, but, you know, it simplifies, okay, it simplifies to t, 4t, 6t. Because we're starting at the origin in three-dimensional space, or R3, 0, 0, 0. Okay, so again, this is very, very similar, guys. Okay, this is simply going to be f of r of t 1 gives me the x, the x value of r of t, r of t 2, r of t 3. Okay, so what I'm really doing basically, if that's hard for you to understand, f of t, 4t, 6t. Okay, but I would get the same answer if I did this, r of t1, r of t2, r of t3. Okay. So, and then I have to multiply this by the norm of the derivative of r of t. Okay, so again, it's very simple. How do I do that? The norm, derivative, I'm going to take the derivative of each element or each component with respect to t of r of t. Okay. Actually, I should close my parentheses right over here. And remember, I'm taking the 2 norm, the Frobenius norm or 2 norm, the square root of 53. So what do I do? Well, escape key, definite integral. Okay. I can, because I'm dealing with it, well, I can pull out my constants, right? So, excuse me. Oops, wait a minute. What am I doing here? Square root of 53, right? And that's 24 times. Okay, so remember, you can, the constant multipliers, you can put them, you can take them and place them outside of the integral sign. Okay, and then here we're going to have t to the power 3. Okay, and that's defined on the interval from 0 to 1. 0 to 1, and this is t. And that's a pretty easy integral to figure out, because really this is going to evaluate to t to the power 4 over 4. The 0 part cancels out, and you're just going to have you're going to have 1 to the power 4, which is 1 divided by 4. So actually, the answer, it's going to be 24 times the square root of 3. The answer is going to be 24 times the square root of 53 divided by 4. So I believe the answer should be 6 times the square root of 53. I'm pretty sure that's going to be the answer, but let's see if I'm right. Or maybe I'm wrong. Okay, so 6 times the square root of 53. 6 times the square root of 53. Okay, easy. I mean, you know, these problems are really not that bad. These problems are really not that bad, okay? So, you know, some of you have the attitude of, oh my God, you know, Mr. Lewitt gave me 100, he gave me 100 of these homework problems to do. Oh my God. Guys, if you study, if you watch my videos, if you read the textbook, if you use Mathematica the way that I expect you to use Mathematica, really, the homework should not be that difficult. It should not be that difficult. I think some of you just, you know, some of you, I hate to say it, some of you maybe expect an easy A or an easy B. And when it comes to mathematics courses, there is no such thing as an easy A or an easy B. There is no such thing as an easy math course. I mean, you know, mathematics is hard. It's a hard subject, and you really have to study. So, you know, that's just how it is. Okay, that's just, you know, that's the world. Well, welcome to the world of mathematics. You know. Okay, let's look at 91. I think 91 is pretty similar, actually. Let's see what we have over here. Okay, convert the line integral to an ordinary integral with respect to the parameter and evaluate it. Okay, so of course, you know, this is, I believe, the second section of chapter 14. This is the second section of chapter 14. Chapter 14 has to do with line integrals, surface integrals, divergence, curl, and some other stuff. Unfortunately, we're not going to have time to cover all of chapter 14. In order for us to cover all of chapter 14, we would need probably at least another 3 or 4 weeks. And, you know, unfortunately, we don't have that kind of time. But that's okay. I mean, we spent a lot of time on chapter 12, but I think that was a really smart decision because chapter 12 is a very important chapter. I mean, you really need to know chapter 12. Okay, you need to know chapter 12. That's not optional. That's not optional at all. Okay, let's get to this problem. Wait a minute. Sorry about that. Okay. So let's see. Clear F and R. Okay, so we have F. Now remember, this is really important for you to understand, guys. We really are dealing with a function of 3 variables. You may say to yourself, wait, I don't see X. You know, where is X? Right? There's no X. So this looks like a function of 2 variables. So how do I know it's really a function of 3 variables? It's a function of 3 variables, guys, because look at the parametrized curve. It has an x component, it has a y component, right? And then it has a z component. So really, I'm dealing with a function of 3 variables in R3. R3 means 3-dimensional space. That's what R3 means. Some people draw it this way. They draw it like that, or they write it like that, okay? Okay, so f of x, y, z, and that's going to be equal to, oh, 1 second, y minus z. Okay, so this is important for you to understand. Just because x doesn't show up in the definition of the function, that doesn't mean that I have a function of 2 variables. This is still a function of 3 arguments or 3 variables. Okay, you really need to understand that, because otherwise some of the stuff in Calculus 3 is very difficult to explain and very difficult to understand. Okay? All right, so this is really a function of 3 variables. It's not a function of 2 variables. Shift Enter. R of t is equal to, okay, excuse me, that was a little bit of a yawn there. It's getting it's getting late in the evening, pretty close to my bedtime actually. 11 times cosine t, 11 times sine t, and then t, okay. And the interval is, okay, t, the lower limit is negative 2 pi and the upper limit is 0. The lower limit is negative 2 pi and the upper limit is 0. So let's see how this is going to work. Okay. Hold on one moment. So for f, I think, oh, let me see here. How would I want to do this? We're just going to use a blank, a while. Let me see if this works. I haven't tried this in a while, but let's see if this works. So we're going to do blank, okay, and then r of t to, oh, actually, you know what, wait. There's no need to even do that because that's, okay, I'm I'm forgetting myself here because that's part of the definition. The x part is ignored. The x part is ignored anyway. So here I'm going to put in f of r of t1, which is going to be ignored in the definition, in the application of the function or the definition anyway, so I'm not worried about it. R of t2, R of t3, okay, and we could make that look a little bit nicer. Traditional form, so that's 11 sine t minus t. Okay. But then don't forget, guys, we have to take the derivative of each component of the parametrized curve. We have to take the derivative of each element or each component of the parametrized curve. If you're wondering how that's spelled, I believe it's spelled like this. Wait a minute. It's a little hard to, I'm using my trackpad to actually write, so this is a little inconvenient. So parametrized, wait a minute, parametrized, Okay, I usually write much better than that, but I'm using the trackpad to manipulate my this software tool. I'm using my trackpad to manipulate the virtual pen, so it's kind of it's kind of awkward. Parametrized curve. Okay, that's how you spell it. Parameterized curve. I believe that's how you spell it. Parameterized curve. And that's this curve right over there. Okay? Okay, so we're going to take the derivative of each component, okay, with respect to t. That's r of t. And just to make sure, I better place this in parentheses. We're going to do the norm of that, the 2 norm, or Frobenius norm. Okay, so yeah, that absolute value. So we can see that t is between -2 pi and 0. T is between -2 pi and 0. So let's simplify that. Okay, so that still didn't give me quite the answer I'm looking for, assuming that -2 pi is less than or equal to t, and t is less than or equal to 0. And let's see if that gives us what we want. The square root of 122, which is what I was expecting. I was expecting kind of a nice answer, a simple answer. Okay, so let's do our definite integral. So that's going to be the square root of 122 times 11 times sine t minus t. And my variable of integration is t, and this is on the interval -2 pi up to 0. Up to 0. Shift enter. Why is there an issue here? Oh, you know what's going on? Okay, I know exactly what's going on. There we go. I forgot my parentheses. Shift enter. Okay, so the answer is simply 2 times the square root of 122 times pi squared. The value of the ordinary integral is 2 times the square root of 122 times pi to the power of 2. It should be okay. Okay. Not so bad, right? Okay, let's look at 92. Okay, how long is this video getting? Okay, we're up to almost 45 minutes. Okay, I'm gonna try to step on the gas pedal and hurry up here, guys. Okay, so again, let's see, clear F and R. Okay, let's see what we have over here. Use a scalar line integral to find the length of the following curve. Okay, this is actually going to be pretty easy to do. So to do this, f of t is really just going to be 1. Okay, so f of t is simply going to be 1. So this is very similar to the previous problems that I did. It's very similar, except f of t in this case is super simple. It's just the number 1. It's the function 1. Okay, so that's pretty easy. So here I have r of t is equal to 24 sine t over 6, t over 6, 24 cosine t over 6, 24 cosine t over 6, and t over 2. Okay, and the interval, t is defined on the interval from 0 to 2. So as we can see here, t is defined on the interval from 0 to 2. Okay? Very simple. Take the derivative of each component. Take the derivative of each component, and I'm going to do that with Mathematica. R of t. Okay, so that's going to give me the derivative of each component, and then I want the norm or the magnitude of this vector. Okay, I want the norm or the magnitude of this vector, which is simply going to be the square root, of the sum of the squares of each element, right? Okay, so remember the norm. How do you define the norm? The norm is, so if I have a vector x, y, z, okay, so the norm, and let's say this is vector v, okay, the norm of v is equal to the square root of x squared plus y squared, okay, plus z squared, okay? And that's true even if x, y, and z are functions of t, okay? Okay, so let's give this a shot. Okay, so once again, Mathematica is giving us, it's giving us an answer that contains the absolute value function. But the absolute value function can make things a little tricky. So remember, guys, we have to tell Mathematica that t is in the interval from 0 to 2. So how do you do that? Full simplify, and then add an assumption, assuming that 0 is less than or equal to t, and t is less than or equal to 2. Okay? So we get square root of 65 over 2. The square root of 65 over 2. So that's really easy. Now all we have to do is do the definite integral. Okay. So that's going to be the square root of 65 divided by 2. And you know what? Again, I had better use parentheses. My variable of integration is t. I'm going from 0 up to 1. And you know what? The answer is simply going to be the square root of 65 over 2. So this is the square root of 65, over 2. The length of the curve is the square root of 65 over 2. Uh-oh. What did I do wrong? Oh, whoa. I know exactly what I did wrong. Okay. Okay. It's the upper limit. Okay, it's not 0 to 1, it's 0 to 2. Sorry about that. Definite integral from 0 to 2, okay, square root of 65 divided by 2, So I believe that's just going to be the square root of 65. So, yeah. Square root, excuse me, the square root of 65. The square root of 65. There we go. Okay, sensational. Okay, we do have time for one more problem. That's going to be it. Let's look at problem number 95. Okay, so this is slightly different. Here, so if you look at the previous problem, let's go back to 92. No, actually, let's go back to 91. Here, we have something called a scalar function. This is a scalar function. So if you look at problem number 95, okay, you're dealing with a vector function. F is now a vector function. So instead of using regular multiplication, we're going to have to use the dot product. But that's not a big deal. That's pretty easy, okay? So guys, 95 is going to be the last problem because I don't want this video to become unbearably long. Okay. The problem reads, given the following vector field and oriented curve C, evaluate, okay, the integral of the dot product of the function f and the unit tangent vector. This is the, I don't think it's just the tangent vector. I think it's the unit tangent vector, which really we've been using all along anyway. And, you know, over the curve, the parametrized curve, ds. Okay. Actually, the parametrized curve is really represented by the capital letter C, and we're integrating with respect to s. So this turns into a regular integral. Okay, so first of all, r of t is equal to 2 plus 9 minus 2 is 7t, 4 plus 8 minus 4t. Okay, so 9 minus 2 is 7, 8 minus 4 is 4. Okay, easy. Okay, and my function f, let's see, f of x and y is given by the vector, one second, yx. Okay, looks good so far. So basically, guys, we're doing almost the same thing we did before, but instead of multiplication, now we're using a dot product, but it's really the same idea. It's really the same idea, okay? Oh, by the way, technically, you know, actually, I should be using s instead of t if you want to get technical. So I should really, well, it really doesn't make that big of a difference, but okay, since S, okay. And the reason is because that's the symbol that they're using right over here, okay? Okay, so f of r of s, the x component, and r of s, the y component. Okay, so that's what I have. Okay, and then I'm going to have to find the dot product of that with the norm of the derivative of each component. Okay, so well, it's going to be easy because it's going to be 7 and 4. It's going to, and actually, you know, if you want to take a shortcut, we're able to do this because R of S has a pretty easy definition. But really, you could simply do this. You could do, so the derivative of this part is 7. 7 squared plus 4 squared. Oh, but wait a second. Wait. That's not, no. I'm thinking about our previous problems, and that's actually not the way to go. That's not the way to go. I don't want to take the norm because then I'm going to end up with a scalar instead of a vector, and I have to have a vector. So what we're going to do for that problem is simply take the derivative. Okay, so it's going to be the derivative of this part, which is 7, the derivative of this part, and the derivative of that part, which is 4. However, okay, now I'm getting myself slightly confused. I believe it's not just enough to find the derivatives. You have to divide each component by the norm of this vector. So the norm is going to be the square root of 7 squared plus 4 squared, which is the square root of 65. So this is going to be 7 divided by square root of 65, 4 divided by the square root of 65, and I want that dot product. And maybe we could simplify this. You know, let's simplify this. We could simplify a little bit more. Well, okay, it's good enough. Okay, that's fine. Here, let me try one more thing. You know, it's really not giving me, okay, hold on a second. Well, it's good enough. It's good enough. Okay, so then I need to integrate this from 0 to 1. I need to integrate this from 0 up to 1. 0 to 1. And this is going to be, 1 second, 36 plus 56 times s divided by the square root of 65. Okay. So 36 plus 56s divided by the square root of 65, and I'm integrating with respect to s, shift enter, and that's going to be 64 divided by the square root of 65. So that is going to be 64 divided by the square root of 65. Okay, so why is this not correct? Okay, I made a mistake. So what is the problem? T is the unit tangent vector at each, okay, so that's, okay, so I think, okay, the problem, okay. So I believe, actually, I think the answer is just going to be 64. I have a feeling, okay, I have a feeling I'm simply supposed to take the derivative of each component, and I'm not supposed to divide those derivatives by the norm of the vector. Although, if I'm dealing with a unit vector, it would make sense to do that, to divide by the norm of the, or the magnitude of the entire, the norm or the magnitude of the entire vector. So that's a little bit confusing, but okay, let's see what happens. All right, I'm going to follow their directions. Not totally sure they're 100% right about that, but let's give it a shot. 36 plus 56s. So yeah, I have a feeling the answer is just going to be 64. Shift enter. Yeah, so I think, okay. Yeah, so what's a little confusing about this problem, this is a little confusing because if you go to the next problem, I'm just going to write down some stupid answer here. I'm going to write 0, okay, which I know is the wrong answer, but I want to see what their explanation is. So if you look at their explanation, it will tell you for line integrals in the plane, let f be equal to the vector valued function f and g, and assume c is a parametrized curve. Assume c is parametrized in the form r of t is equal to x of t, y of t in the form of a vector, where t is defined on the interval from a to b. So remember, remember the word is parametrized. Parametrized. Fancy word, right? Then the line integral, okay, this line integral right over here, let's see, may be expressed in the following forms. Okay, so this is actually what I used. This is what I used. This is the form that I used to solve the last problem. Okay. But it's interesting because this is actually the tangent vector. Okay, but I suppose it doesn't have to be a unit tangent vector. Okay, so that was my mistake in the last problem. So my mistake in the last wait a second. So how do I go back to the last problem? So, oh, come on. Okay, so my mistake in the last problem was assuming that this had to be turned into a tangent vector. So that was my mistake. So, well, it is already a tangent vector, but it's not a unit tangent vector. Okay, so now I understand what's going on. So, excuse me. So we have a vector here, 7 and 4. And actually for this particular problem, okay, this is t, which is actually a tangent vector. It's the tangent vector for the parametrized curve is really what it is. So if I were to do this, 7 squared, which is 49, okay, 4 squared, which is 16, okay, and then we have 49 plus 16 is 50 plus 15, so that's 65, the square root of 65. 1 second. So then if I did this, I'm running out of space here. So if I did this, 7 divided by the square root of 65, and then 4 divided by the square root of 65, okay. These two vectors here are very, very similar, but the difference is this is a unit tangent vector, whereas this is not. So, okay, so my mistake when I was doing this problem was assuming, although I could have sworn I read that in the original directions for the problem, but okay, maybe that was a mistake. Someone who works for Pearson may have made a mistake with that. This does not have to be a unit tangent vector, okay? This does not have to be a unit tangent vector, simply a tangent vector. That's it, not a unit tangent vector, just a tangent vector. Okay, so it does pay to read directions, right? Okay, guys, I think this video is definitely long enough. We are up to, let me see here. How long is this? We are up to a little more than an hour. So I think, you know, we've done enough here, okay? So hopefully you understand what is expected of you. You should know how to use Mathematica to make the homework problems, easier, and you really should not have any difficulty completing this assignment on time. And remember, our semester is almost over. I think the last day officially is December 16th, but I will probably extend your quiz and test to December 17th. But you need to get the homework done. You need to get the homework done because it would be fantastic if you would do the quiz and test a couple days earlier, because you don't want to wait until the very end. That's not a good choice. You don't want to wait until the very end. You want to get this stuff done as quickly as possible. Okay, guys, that's it. Have a wonderful weekend, a wonderful day, a wonderful whatever, and give yourself a break from your studies. Get some exercise, get some fresh air, go walk your dog, do something, get some exercise, and do some yoga, do something, and we will communicate at some point in the future. Okay, take care, and that's it for now.